Okay, perfect. So good morning to all of you. I'd like to welcome you to today's web seminar on the FEM planet carrier and the FVA-Workbench. A few words to myself. My name is Georg Hammerl. I've been working now for more than 4 years at the FVA company, and I'm responsible for the finite element topics. So I'd like directly to start. Oops, sorry. Just a few words. What is the FVA Workbench at all? I will keep it brief here. We had a webinar approximately 4 weeks ago. There, all the details about the possible calculations have been summarized. So if you're interested here in more details, I refer to this webinar. You can find it on our website. And here I would like just to summarize, it's a software tool that allows you to calculate more or less all machine elements that you have in your transmissions or your gear unit system. And what is quite interesting, our users are very often experts on gears or bearings or on their machine element, but sometimes they're not the experts on the finite element method too. So we try to keep it as simple as possible when finite element bodies come into play. And we try to set up processes that are as fail-safe as possible. So even if you do not have that much knowledge, we will try to get you at the solution you expect. And here our slogan is one-click FEM, so really keep it as simple as possible. Today we will focus on the planetary. You can see it here, but it's also possible to include the gear casing as a finite element mesh, the wheel bodies, and the shafts, because these are the components that can be quite complex in geometry. So here the finite element method is favorable compared to purely analytical models. Here I'd like to show you why I think it is important when it comes to the planet carrier to use finite element models instead of purely analytical modeling approaches. The first reason is the side plate can have some deflection modes, such as warping of the side plate itself, which is hardly to capture with the purely analytical model, because usually for shafts we use a Timoshenko beam model, meaning it's a 1D model just on the center line, and 1D model is not capable of having such a deformation mode. Also, the geometry can be quite complex. So if we think about the strut geometry, so strut is what connects the left and the right side plate. It can be formed quite difficult and complex. So there it's also hard to find a good analytical description of how it should be modeled. The third thing that comes from the modeling, so this is here the stem shaft on which the side plate is mounted. In the purely analytical modeling, we couple here the stem shaft and the coupling to the planet pin rigidly with a rigid lever. And if we think about what will happen in reality, so imagine here this like a one-sided clamped beam. So here is the clamping of the beam, this is the beam, and if you apply some force here in tangential direction, one would of course expect that the beam will deflect a little bit, and this is exactly what the planet carrier does in reality too. So in order to capture such a motion, it's favorable to have here finite element models. Then I would like to show you a small difference, a small comparison that we did. So I mentioned we use a Timoshenko beam model for our shaft, and we did a quite simple setup. So having here a shaft, having a bearing left and right side, so it's a symmetric setup, and a load in the center. And we compared our Timoshenko solution with a finite element solution in the way of reduced stiffness matrix as we use it in our model usually. And we see in case the diameter, so here it's the deflection, the maximum deflection of the shaft over the diameter ratio. Diameter ratio means here the diameter in the center compared to the diameter of the shaft on the outside. And here on the right side, the jump in diameter is larger. And we already see, or better say, in case there is no jump in the diameter, then the results are more or less equal. And in case there is a jump, we already see a difference in the maximum deflection, approximately 20%. So this is quite interesting. It already shows that the Timoshenko beam comes to a certain limit here. And when we zoomed in a little bit, we found where the difference usually comes from. So here is a deflection that a Timoshenko beam in its 1D representation cannot capture. So here the finite element model behaves a little bit softer and shows more deflection. But now I'd like to come back to my planet carrier. I would like to show you which possibilities you have to include the planet carrier in the gear transmission system. So the first variant is, which is very common for our users. We have an already existing CAD geometry. We have an internal FEM measure, including a component defeaturing capability, meaning that we can remove tiny pores if they lead to a distorted mesh. I will show this later on, how this means in detail. Then the next step is apply the boundary conditions. So first do the positioning and then determine the coupling nodes. This is something I will show later on too. Then the reduced stiffness matrix and reduced load vectors are computed and stored in the model. This is essential because then in the following steps, the calculations are done. You can vary your parameters, but the reduced stiffness matrix will always be the same. So everything that you see here on this, it's more than the half. So on the left, 80% is a one-time cost, and this can be repeated very often, very fast. And this one-time cost is only necessary once. Another option to start is from our parametric CAD generation model, meaning that you just provide a few diameters or width parameters with values, and then you can use our internal 3D CAD kernel, which creates these geometries automatically. So just by giving a few numbers, you end up already with the CAD geometry internally. And then we also use again our internal FEM measure, and here the same workflow. The third option to start is from an already existing FEM model, so an FEM mesh. This might be interesting for you if you have from your calculation department some meshes. You can directly import them in the FVA-Workbench and couple it starting from here to the remaining model. This is one slide to show because most of you have already, or all of you have already used FVA-Workbench, are used to our right-click menu. So in the model tree, as can be seen here, we have the right-click menu, and there we have so far all the content that is related to the finite element and CAD body handling. It was a little bit unordered, to be honest, and that's why we have reordered and rearranged this. So now there's no longer the right-click menu responsible for these actions. It's gone to the editor, and there we have now these steps. So meaning it's really clear, step 1 to 5, you need to do this. You need to do it only once, and you can see which body you have included. These are all things that have been missing here. So I reordered the whole thing, and also the choice, do I now use the analytical modeling, so without FEM, do I use imported CAD or FEM geometry, or our internal modeling? It's way more obvious what happens. So please don't wonder if you see now this layout, because I will work today in our development version. So this is what will be released in summer. And this will also be the future here. So this is for you what you still know, but this will be what you can see in future. Now I'd like to stop here with the presentation and switch to the FVA Workbench because now I'd like to show you with 3 different models interesting aspects that might be new for you, even if you have been maybe working for a longer time with FVA Workbench. And just to show you which options you have. So what you can see here is a wind turbine model. So we can briefly hide the gearbox and have a look at the transmission system. So it's here in the beginning planetary stage. Usually the rotor is mounted here in front. Then we have an intermediate stage and the high-speed final stage. And I would like to focus now on the planetary carrier and which options you have here. I will show you the workflow with the import of the CAD geometry. So let's show the casing again. Let's switch to the planet carrier. And as I've shown you, the planet carrier has now here the option between analytical modeling, which just means specify a few stiffnesses that are used to couple the left and the right side plate. And that's enough. You don't have more options here. And I would like to go to the import CAD or FEM geometry version now. So let's import the CAD body. Usually many of our customers work with a step file, but it's also possible to include different native formats, CATIA, SolidWorks, Solid Edge, Siemens NX, Pro Engineer. So the most important ones are available here. So let's import the CAD geometry, and then you're asked in which unit you have constructed your CAD model, because it needs, of course, to fit our internal units, which are millimeter. So here maybe a conversion can happen, but this is done automatically. Then we see the CAD body usually lies in a completely different coordinate system than our internal coordinate system, but this is not a problem. Therefore, we have these steps here, which will then do the aligning and coupling. But in the first step, I would like to mesh this geometry. So let's start with run FEM measure or step 1. Then we get a focus here on the CAD body. And our internal measure allows you to create the FEM mesh. Just a few words here, what you can see. So for example, if you have a look at one of these bores, which is used for bolting the pin. So here it's just to show if you use this defeature slider, have a preview here on the surface mesh, we will see that these bores are removed, so they're fully meshed. By just having 3 of them, it's not relevant. We can stick to a slightly finer resolution, and we will see that they are quite good resolved. But in case of a gear casing, let's assume hundreds of tiny bores, they might lead to really distorted and nasty elements, leading to problems with the FEM solver. There it might be very interesting to remove these tiny bores, which are fully irrelevant for the stiffness of the model, but they lead to problems in meshing. So if you have a look at this mesh here, this is a good compromise of having resolved the features and not being too fine, because it takes, of course, more time if you have a finer mesh. So here you've seen that's the second important slider that allows you to refine or coarsen the model. Then we can create the volume mesh, and what will happen is here in the 3D view, the CAD body is replaced by the finite element mesh that we have created here. Then already the next step is the positioning, or let's have a brief look at the element quality. So we had an FEA project which gave us the option to investigate a little bit in detail what is the element quality of the model. So here it says us roughly 0.5% of the elements does not meet the element quality criteria. So we can do this optional step 2 here, run this quality checker, and then you really get a view on those elements who are distorted. So it's recommended to have them a little bit lower in number, these distorted elements. And what is also very interesting, there are so-called critical elements. They're super flat and usually lead to a failure of the FEM solver. So there should be none of them, which is good here. And if we switch to the second option here, we get all those elements which are critical and unqualified. And the unqualified, these are now these 0.577%. And we can see where these elements are lying. And the geometry has here some small grooves. And in these grooves, the elements are very flat. So this is something that we will have also a problem with even finer mesh to get resolved. But this is something I would accept. But if you want to make it sure, then choose the finest solution and compare the results via using the fine mesh, and in this case here the very fine mesh. And usually it turns out that the results are nearly identical, and then you should stick to the coarser one because it's of course a little bit faster in handling. In this case, we stick to this model here and continue with our step 3. So let's do the positioning. Oh, I'd like to share something too. Here the casing might be annoying because it is always in our view. So what I can recommend here is just go to the casing, use this consider calculated FEM stiffness checkbox, and then it is removed from the model for a moment. We will get it back later, but for handling now it's a little bit more convenient here. So now let's do the positioning. And what I expect you from here as a user is, because this aligning, I need information from you. You need to select 3 nodes on an edge of the FEM mesh, and it should be an edge because I do know what I do not recommend. If you choose here on the inside 3 nodes, you also get a circle that goes through these 3 points. But depending on the measure, so if you have a look, for example, here, this won't be the perfect circle I'm interested in. So I always recommend use a real edge of your geometry, and then you can make sure that this center line that you get is really what you expect to be where the axis of the central shaft is located. Then we choose one of the central axes, and we see now we have already aligned the central axis. We could reverse the axial direction now directly, but it should be the other way around, of course. So you see that this is what we will end up finally. But for a moment, I will keep it in the wrong direction so I can show you how it's easy to reverse it later on. So let's stick to this here. Now in the second step, we need to align the planets. So again, where one planet is, we need an edge on which you please select 3 nodes. You get the center line automatically, and then you decide which of the planets should be aligned to this position. So in case they are not equally distributed in the circumference, this might be very helpful and also necessary. And in this case, it doesn't matter. So now it's here on the back side. Where is it? Okay, so we can switch this through. In this case, it doesn't matter. So we take this one. And now I came to the point where I say, oh, it's in the wrong axial direction. So I just go back the 2 steps to the reverse axial direction, click on apply. Next, now we need to apply here too, so make sure that it's correctly positioned. We move it a little bit away from the model, so it's clear where we need to click later on to find the last FEM node. Apply, and next. Now we come to the point where we have been right before, and we need to do the axial positioning. This goes in a way I offer here the couplings. So the couplings are the connections in our analytical model between different parts. And here's, for example, the coupling between the pin and the original side plate. Here's, for example, the coupling between the ring gear shaft and the housing, and so on. And you get here the couplings that are related to the planet pins and to the connection between the stem shaft and the original side plate. So here we only rely on them as I call it geometrical support. So the diameter and the width are relevant for me, and I use this information for positioning and later on for snapping the nodes. But this will be part of step 4. So now we choose a single node where I know the position relative to one of these couplings. So I know, for example, the planet pin will be mounted such that the planet pin touches the surface. Then I choose the coupling to get the planet carrier over here. Usually I cut through here, which helps to see that the positioning is accurate. And now we can more or less play around. So which coupling is the correct one? So this one, for example, is here on the left side of coupling, so it's the wrong one. Let's zoom in a little bit. And we see now the surface touches. This is quite good. This coupling 35 would be a coupling here between the original stem shaft and the side plate. So this is not the one. I know that here the axial aligning should take place. So let's take here this coupling 38. In case this does not match, you need to adapt the width or the position of this coupling, of course. But for now, I'm happy here. And just one word to this left-right. It's of course not clear a priori if this aligning should happen on left or right end of this coupling. So you can choose here the correct one, but you see by having a look at it which one is good. So then we are done here. And now the finite element mesh snaps to the correct position. So what we did so far. Then I would like to come to our step 4, snap the coupling nodes. What comes here is very essential. You need to specify which analytical parts, so in this case the shafts on which the side plates are mounted, are part of this FEM mesh, so which are included. I will focus on this later on when I talk about the internal planetary modeling, but here always important, keep in mind this needs to be checked correctly. In case the planet pins, as shown here, would also be part of the defined element mesh, then you need to check here also the pin. And I can show you what happens if you do not choose here properly. So let's come to our model, automatic determination of the coupling node. We can hide the full gearbox, and now we already see, so these small squares mark where the coupling is assumed so far. So for example, here is a bearing. Under the bearing, the nodes are snapped. Let's have a look here at the other side. So here's the same bearing and nodes are snapped. Also where the pin is mounted in the planet carrier, nodes are snapped. But this model is actually quite interesting. So it's an external model. I'm allowed to show it. it seems as if here the bores are not perfectly cylindrical. So, but this is actually a good model to show how the tolerances are can be used. So you see here, not all the nodes around the circumference where the pin is sitting are snapped. But if we increase the tolerance here a little bit, we see more nodes are snapped. And if we increase it even a little bit more, now we see all the nodes, the circumference are snapped. That's why I actually like this model, although it's not a perfect model, of course. Okay, so this is good so far. And I always recommend have a detailed look at the nodes that are snapped, because we'll see here, for example, the planet pin actually covers the full width of here where the side plate is, but the nodes are not snapped over the full width. So what the problem here is, I mentioned I rely on these couplings. The coupling does not cover the full width, and that's why not all nodes are snapped here. So we need to adapt this and increase the width a little bit. Second thing that I'd like to show you is here where the bearing is. So let's cut through for a moment, zoom in, and we see here's a small gap. So the position of this bearing is not perfect. So if I hide the gearbox for a moment, we see these nodes are snapped, but not the nodes here on this shaft shoulder, but they're actually the axial force is applied. And I always try to catch those nodes where the real geometry touches in reality. And therefore we can adapt this here too. And the third thing that I'd like to show you is the load. So in a purely analytical model, this load is sitting on this analytical shaft. It's okay. But here, of course, because this analytical shaft is removed from the model, I need to transfer this load to the FE mesh, meaning that I need to snap all the nodes here on the FE mesh in order to apply the input torque here. It's favorable to have these nodes distributed as equally at the circumference as possible, but of course the meshing algorithm is not always helping here. So I'd like to show you an option how you can improve the situation here with the dummy shaft and coupling that allows to snap really where you'd like to. But for a moment we keep this. Let's finish the whole thing. And let's now adapt all the things that I've mentioned where I'm unhappy with the model. So let's first start with the coupling here. We saw not all nodes were snapped across this width. So we can have a look here at this coupling. Coupling has a geometry, and I always recommend for those couplings you use for snapping the nodes, choose inner outer diameter to be the same, and adapt the width as it is necessary. So for example, we increase it to 90 millimeters, and when we will see the coupling goes beyond this outer surface of the planetary, and when we re-snap the nodes, we will see that all nodes are snapped. Then also let's have a look at here the bearing. We saw that it was not perfectly aligned. So let's zoom in a little bit and let's shift it by 1 millimeter, and then we'll see now it touches, and we will see when we snap the nodes that no more nodes are snapped. And regarding the load, I mentioned this is an option just to take the nodes that are snapped here, but I'd like to show you my more favorite version. So let's have a brief look at the load. It has 1.5 megawatt on power, and it is the input. So let's throw this one out, and let's insert this dummy shaft that I mentioned. So we go to our plate. So to make it more obvious what happened, I switch back for a moment to my analytical modeling approach, and we see this is what we did in the original version without FEM. And then we can add here a coupling, and with this coupling we add a new shaft. Material is more or less independent because it's a dummy shaft anyway. We position it at the beginning as this plate is, and we set this here to 0, meaning that the position of the clutch is right at the beginning. Then we can include this, and we see now the small shaft here is included, so we need to adapt the geometry a little bit. So let's have here the diameter of where, so it is more or less independent. What we said here, it's as mentioned just a dummy shaft. More important to me is this coupling, because this coupling I will use for snapping the nodes. So let's have here the shaft, and let's have now the geometry specified of this coupling. So let's have 600 millimeters. Let's have a width of 100 millimeters, and this width will be relevant for the snapping, of course, now, and also the diameter. Then let's shift the coupling a little bit by half of its width. And to complete the model, we go to the gear unit, to the power flow, and there we have now our dummy shaft. So you see an output is specified. The input has been lost because I've thrown it out. So let's have here the input, and let's have the 1.5 megawatt. The power flow has been completed, and I can go back to my model, switch back to imported CAD or FEM geometry. Now we see again the FEM mesh, and we see I have now this coupling here exactly at a position where I can now do the coupling. So if we do our step 4 again, so any step can be repeated at any time. It's only important at the end you need to compute the reduced stiffness matrix to be saved in the model. We need to check again these two plates, and if we do now the automatic determination, we see on the one hand, so let's again increase the tolerance a little bit. We see now here we cover the full width because we increased the width of the coupling. If I have a look here, before these nodes weren't snapped because there was just an axial offset of the bearing. So now there is snap 2. And we see here this is our dummy shaft, and on the dummy shaft is this coupling, and exactly where the coupling is, the nodes are snapped. So you can decide by tuning your couplings where you expect to be the coupling to the final element body. And just one short thing, if you do not properly set these checkboxes here, and we do a automatic determination, then, for example, under this bearing, there, oh, sorry, this is included. Oh, one of the couplings, exactly, because now I assume that the coupling is at a different point, so the original shafts are remained. And then I search at, of course, a different position, which is not correct. So it is correct here because your model includes both of these shafts, your FEM model, to have this choice, and then you don't get a warning error, and you are happy. So let's finish the whole thing. Now we can conclude with our step 5, meaning that the reduced stiffness matrix and the reduced load vectors are computed. They are stored in a model and can then be reused for further investigation of the model. What I will show in the following minutes is how an easy comparison is possible. For example, of your finite element planet carrier compared to your purely analytical modeling approach. So we can just insert our casing here again. So now we would like to compute the whole thing. So let's include it again. And we see we have now planet carrier and the finite element mesh for the gear casing. And one special thing I'd like to point for a moment. Here is one bearing that is located between two finite element meshes. So also such constructions are possible. Now let's run the whole model. So we compute the complete system, meaning that now the deflections are computed. So it's a quasi-static analysis that is done. The torques are applied and all the boundary conditions are taken into account. For the shafts that are not FEM here, Timoshenko beams are used, and the bearings as well as the tooth contact. There, this nonlinear Hertzian contact is modeled, but in an analytical way. So these are super fast models. They have been developed in the FVA over decades now, have been compared against experiments, and they're in use in a lot of companies. So these are really sophisticated and fast models. But the Hertzian contact is of course nonlinear. So what is solved here in the background at the moment is this nonlinear system of equations. Then we're done here with the solving. We can give this solution here a name. So this is the solution with FEM planet carrier. Store the whole thing, and here on the left bottom we see all our, we call it snapshots. So these results are stored here. And if I'd like, for example, now to have the comparison between the solution that we have here with the solution with the purely analytical modeling, I can switch here to the analytical modeling. We see it's similar model, the whole thing, but these strut geometries are missing. Therefore, we have the stiffnesses. So in this case, I do not plug in more details. So we assume that these two side plates, the left and right one, are coupled fully rigid by having these large stiffness values here. So there would be the option to have rotational stiffness, bending, radial and axial stiffness between these two side plates, and this would be a surrogated model for the strut geometry. But now let's run the simulation. What you can also see here on the bottom is we have this messages window. There you get information whether everything works correct, or in this case, it seems as if something with the gears is not yet okay. This is something I won't focus on today. This should be, of course, repaired, but here I refer to following webinars that will come, or to the seminars that we also offer. There you get more details on what's going wrong here and how to solve it. I would really like to focus here on my planet carrier today. So system is in its solve, and then we get again the option to set the name here. We get the second snapshot, and then we can do the comparison, what is quite helpful. So let's give it a name. So this is without FEM planet carrier. Now we have these two snapshots here. I can set one of these as a reference. So let's say the analytical modeling is my reference. So set as reference here with right-click menu, and then do a comparison with the reference. And what happens now is an HTML report. This diff here is generated, and it's opened in my default browser. So because it's an HTML file, it's very favorable because you can store it on your machine. You can send it via email to someone else, and this person can then have a look at the results that we have now, even if this person does not have FVA-Workbench installed. And some sales representatives in the companies sometimes directly use these reports. They just open their laptop and then show the reports. For the planet carriers, it usually takes a few moments. There are many machine elements included, but then automatically this comparison opens. And we see we have here now two columns. Right column is without the FEM. We see it here in the picture. and the left one is with the FEM planet carrier. And what I like very much is we can focus on the differences only. So we check this here, and then we get a highlight on all the differences between these two models. I would like to point here on the pin. We had the two side plates coupled rigidly. So if you have a look here, these are the tilting values where the planet pin sits in the planet carrier. And if we have a look here at these values, so we see if you compare this one with the version with FEM, so the FEM version is factor of 10 softer, because here the two side plates, they can deform relative to each other. There's of course the struts in between which hinder this deformation, and the pins are clamped. But this purely analytical modeling without specifying certain stiffnesses, which are not that trivial to get, to be honest, it gives us a solution that seems to be a little bit too stiff. And of course, also if you have a look at one of the stages, so for example, Sun Planet, let's scroll down a little bit and have a look at the load distribution. We see, of course, this tilting leads to different load distribution across the gear width, and therefore this tilting is essential here. Okay, so I'd like to stop with this model here, come to my second model. So let's switch to the internal planet carrier modeling. I have a very simple model here, just a single planetary stage. Go to my planet carrier and switch to now internal FEM planet carrier geometry. What I directly like to show you is we can now immediately run the FEM measure, and we see now only the side plates are then treated as the FEM model. So we can here directly create the volume mesh. Here the meshing is very trivial, so it's not a problem. And you see all elements complete the quality criteria. So this is not very difficult here. And I would like already to run my simulation now. So let's switch here to the calculations options, and let's for a moment activate the FEM body deformation so we can have a look how this deforms. Let's complete our steps. I skip the mesh quality, snap my nodes. This is here, can't be altered here because in the internal modeling approach, I know what is correct here. We detect the nodes and we see where the planet pins are included. There the nodes are snapped, and also at the full circular cylindrical geometry. So this was really a thing of our model in the beginning that I imported, that I had problems here. And here these nodes are snapped where the couplings to these two analytical shafts are. So one could either have one bearing here on the right and the left side, or as here, the bearings just on one side. And we see now the nodes are snapped here. So let's finish the whole thing. Let's calculate the stiffness for these tiny models. This is really fast. And now we can compute system deflection. Can again store then our snapshot. So this is base side plates only. And we can have a look here at the gear deformation. So let's reduce the scaling factor a little bit. Let's activate the FEM deformation. And let's focus here on the planet carrier. So component representation to solid with edges. Let's throw out these deflection curves. and let's increase the scaling factor a little bit. Then we can already see this warping that I mentioned. It's of course quite pronounced because there are no struts in between, and only the pins lead to or hinder the torsional relative motion. So here there's quite a lot of this is warping deformation. That's why I would like to include in my model now these struts. So we throw out the mesh. We add this checkbox, or we check here the detailed strut geometry. Then we get all the details and we can start, so we see them already here. We can adapt here the geometry, how we would like to. So, and then what I else would like to show is if I change here the number of planets, then you automatically get the corresponding positioning of these struts. So, for example, here this would be a little bit too tight. This is not good. So let's increase the inner diameter a little bit. Okay, so this is better. Let's here also adapt the width a little bit. So this might be an option. It looks better, the whole thing. And if we would be happy now, we could directly run the FEM measure. And what we see is right before we only had the side plates. Now we also have these struts included. I do not conclude the meshing here because I would like to point this option here in the middle, which is very common. So you fill this radius of planetary gap, and you see you get the surface, the geometry following the tip radius of the planet gear. So if the clearance is not enough, you might increase this a little bit. In case you have a welding construction, it might be interesting to set this wall thickness here, because then, so let's just open it on both sides, then it can be seen better. So this may be welded in between the two side plates, which might be an option. Otherwise, if you don't like it, you throw out this by just setting the 0 and you get full material, which is fine, of course, too. Then let's now snap. Oh, sorry, I forgot to run the measure. You see we have checks everywhere. So we bring you to the solution that you would like to have. So we have now the mesh, we snap the nodes, and here now same nodes are snapped because only the struts are included, so no changes here. We can compute the reduced stiffness matrix and can directly run our system deflection. This takes again a few moments. We can also change this later on. This is now with strut, and I switch to for planets. Then I would like to continue with the next version. So I again throw out the FEM mesh. And now I'd like to show you what happens if you insert here the stem shaft. So these plate 4, plate 6, these are the two analytical shafts. If I check this here and run my FEM measure, then I see now we're getting closer to what we had in our first model from the wind turbine. The two stem shafts are included. We have strut geometry and the side plate. So let's create the mesh. And what is important now is if you have a look at the nodes that are snapped, now you see these two checkboxes have been checked. It's done automatically here. And we see very similar to what we had in our wind turbine model. Here, the nodes are snapped where the bearings are located. And at the same time, there is no longer a coupling here because this is purely FEM. So no nodes are snapped here. That's why told that it is really important to set this correctly, especially in this case of imported cut or FEM geometry, because this then really leads to a difference in which nodes are snapped, so the coupling is either correct or it isn't. Okay, let's finish the whole thing. Let's calculate the stiffness. And you see for those models having not that much elements or nodes, this is a very fast task. We can run our system calculation and do again a comparison. So this is now with stem shafts in FEM, and let's have the 4 planets with strut as my reference. Do a comparison. Then we can already see what is the difference when we have the same geometry, but once computed it with analytical stem shafts, and in the other case computed with purely FEM. So it takes a few moments again until it is loaded. And if we have a look now, the differences only, what is quite interesting here on each of the loads, so here in the input and output, you can have a look at which torsion angle your model has. So where 0 is the output. The output is always fixed, so there is 0. And on the inputs, you see which angle you get due to this torsion of the full transversion system because it's loaded. And we see with having the FEM part being bigger, so having this first plate included, then the model behaves a little bit softer, and we have here a little bit more torsion. What else I'd like to show you is if you have a look at this plate, so in the right view, it is included. In the left, it's part of the FEM. And we see here our bending lines on the left is nothing because within the FEM model, we do not plot any bending lines because it's just not possible. There is no single central line that we can use for plotting bending lines or also the force values. So here you usually find nothing if you include it, and please don't wonder here. The last option I'd like to show you is what happens if we also integrate the pins. So let's again throw out the FEM mesh. Let's additionally set this checkbox for adding the planet pin into the FEM model. And let's run the FEM. One thing that I'd like to show you also, I almost forgot it. You can export this geometry, meaning import, export 3D model step. And then you have the option to export parts or the full model. And for example, if you have a look here at our struts, the plates, and for example, the side plates, and if we exported it, give it here a name, export PC2. It is exported. Let's close the whole thing. And I have just an arbitrary step viewer here. We can now open this PC2 that we have just created. And let's have a look at it. Well, this is exactly the geometry that we've exported, and it might be an option for you. Take this as the base for your construction, do the further construction, and then go back here and import this final CAD body as we've seen in our first wind turbine model. And then you can do a comparison of what you did here with the internal modeling and compare it to the solution that you had after finishing your construction completely. But I would like to run my FEM measure now. Oh, give me a second. I missed something. Okay, that's good. We see the planet pins are now included in the model. And this is especially interesting, this having the pins included when you import ECD geometry, where it's not clear to distinguish between where is actually the side plate, where is actually the planet pin. Here it's super clear where the distinction is, but your construction might be really complex and then it's no longer clear. And then this is a really helpful option to have the pins included. The only thing is you need to keep in mind you can only specify one single material here. So there's a small drawback at the moment, and you need to keep this in mind if you use this modeling variant. This was now a very trivial model, but it helped us, I think, to see the differences where the nodes are snapped. And this is also what I'd like to show you here. So now also this pin is checked. If we now have a look here in our model, we see nodes are snapped where the bearings are, and now the nodes are snapped where here the planet bearings are sitting. So the planet pin is part of the FEM model, and now the coupling to the analytical model is here where the planet bearings are. So if we hide a few of these components, we can see this quite nicely. There's the planet shaft, and we see here the two bearings, planet bearings, and if we hide them, we see, okay, here are the nodes snapped. So this is what you should check. Now I'd like to finish with this model and come to my last model. This is just to show you what is really possible. This model that I'd like to show you is from the student racing team of Karlsruhe Institute of Technology. I was allowed to show the model to you, and this is now a model that has, I would say, real complexity, because this is what I've shown you so far, I would say more or less trivial. But here in this model, it becomes obvious which options you have. So on the one hand, it's a super lightweight construction that you can see. And I cut here through for a moment. That's what you can see is a planet carrier, but you can cut through it, then you can see it better. So where is it at cutting plane? And then, so the model is a little bit larger, so it's no longer that fast. But what we can see is here, so this is the input. Here's the first planetary state. This whole thing is still standing. So the sun drives the planets, and the planet carrier drives the second sun. Here the planets are still standing, and the ring gear is where the wheel is mounted, and the wheel is driven. So if we have a short, and this big thing is then modeled as the planet carrier. You see it here, the planet carrier of this second stage. And again, bearings between two FE meshes. This is possible. And we can have short animation. So let's remove cutting plane and let's then run the animation. Then it gets more obvious what happens here. So let's reduce the speed of the animation a little bit. So here we see the whole thing is still standing. The ring gear is turning. And on the other side, because here's second FEM planet carrier, we see it turning around. So the sun is driven with an electric engine quite fast, actually. And so the speed is reduced, torque is increased with this construction. So this is only to show you how complex models can be. So you can combine as many machine elements here in stages as you'd like to. Wolfram stages, Ravignon stages can be included. So here you're fully free, and in all of these the planetary stages, you can insert the shown planet carrier FEM options. So I think we're quite good in time, one thing that I'd like to still show you, then I have concluded everything, is let's go to a coupling between the planet pin and the side plate. This is something that you might not know, especially for those who are familiar with the FVA-Workbench. You can specify for each of these couplings, or also the planet bearings, if you have the planet bearings mounted in your side plate, certain displacements. So if you know the tolerances of your manufacturing, you can analyze this here by setting here the lower, the upper tolerance, run the analysis, and then compare what the tilting and load distribution does. So this can be quite interesting. But now I would like to thank you for your attention. If there are any questions, you can write them in the panel. I will then answer them. And if there are no questions, thank you a lot for attending this web seminar. And I hope you learned a little bit. And if there are any questions, you can also come to me afterwards, write to our support, have a look on our web page. So give me a second, I can show you. A web page. It's just www.fva-service.de/en, and then you get more information. But now, if there are any questions, please let me know.